All right, so from last time, we were finding the normal force of the ladder on the wall. So we are sitting here with 1/2 times the weight times the cosine 60 divided by the sine 60. So, yep. So we have 1/2 times, what is the weight?
You don't know the weight.
We don't know the weight. So what would the weight be?
The weight's going to be M1, negative M1.
From here, we can calculate the weight, and it is normal 1. So weight equals normal 1, or normal 1 equals weight. So how does that help us?
We know that normal 1 is just we need some sort of equation to solve for normal 1.
Okay, so what is it that we're doing is a good question. What is it we're trying to find?
We're trying to find the coefficient of friction.
Yeah, the coefficient of friction.
What is the coefficient of static friction? That's mu sub s that we're looking for, right? And we have not talked about mu sub s yet. Okay, so as of right now, we have normal 2. And actually, we can simplify this. You guys mentioned that cosine over sine is what? Cotangent. But the reciprocal of cosine over sine is sine over cosine, which is tangent. So I'm actually going to rewrite this at normal 2. The 1/2 could be written as 1 over the 2 in the denominator, right?
Yes.
So this could be w in the numerator, 2 in the denominator, and then instead of writing cotangent, which would be in the numerator, I'm going to put tangent in the denominator. So this is tangent 60 degrees in the denominator, okay? So that just makes what we're dealing with here with this ridiculous normal 2 way simpler looking. All right, so now the weight is normal 1. So instead of writing weight, I could have written normal 1. So we're going to keep that in mind as well. Now, how do I get static friction's coefficient involved in this somehow? We got to kind of remember back a couple of chapters.
Will that be N2, right?
Is it?
N2 is going to be equal to static friction.
Okay, so static friction is down here. We have a static friction force,
which is the coefficient times normal friction.
Static friction, let's see, let me choose a color. Static friction is equal to what?
U sub s.
Mu sub s times,
In this case, yeah, it's
the normal force?
Yeah, normal force.
Okay, which is mu sub s times the weight, right?
Yeah, weight.
Normally mg, which we just said was the normal force. So that's normal 1. Okay, so we have mu sub s times the weight. All right. Now, the static friction force is going to be exactly equal to, or since it's static friction, is it going to be greater than that, or is it going to be less than that?
It's going to be greater.
If we're talking about minimum value.
So it'd be less than.
It's going to be less than. Remember that the static friction force is exactly what it needs to be to keep the ladder being held in place. It's going to increase up until the breaking point, and then we're going to have kinetic friction as the ladder slides, right? So it's going to actually be, I'm going to rewrite this, F sub s is actually going to be less than whatever the mu sub s, less than or equal to whatever the mu sub s weight is. If we think about it that way, then we can talk about minimum value, okay? Not that it matters a whole lot, but that's sort of the reality of what's going on here. Now, is it mu sub s, is F sub s going to be equal to normal 1 or normal 2?
Normal 2.
Why?
Because of your sum of the forces in the x direction.
Yes, sum of the forces in the x direction says F sub s equals normal 2, actually. Okay, so from that one, we now know that F sub s is normal 2. So
we can plug in F sub s as N2. Correct?
that's right. Now we have a connection. We can bring F sub s down into normal 2. Okay? So now that we have that knowledge, I'm going to come down here with F sub s for normal 2.
And since we've solved for that, we can put
And F sub s is just
W
mu sub
over
s times
2
W.
tangent 60
Yep.
equals mu sub s W.
W over 2 tangent 60 degrees. And that is actually less than or equal to, right? That's what we said earlier. Less than or equal to
Mu sub s
mu sub s
W.
W. Now what happens to the W's?
Divide out.
We're going to divide them out.
And now we can solve for mu sub s.
So now we can solve for mu sub s. Really, we have mu sub s is 1 over. So if I read this backwards, I have mu sub s is greater than or equal to 1 over 2 tangent
Let's see.
60 degrees.
If I pull out mine.
And make sure you're in degree mode on your calculator. And we can come up with an answer.
It is root 3 over 3.
Yeah, but we want a decimal here.
What over 2? 3 over 3, which is
0.288.
0.2887 to 4 decimal places. Okay, so there's your answer. So minimum is that number, and then it's just going to be bigger than that somehow. Okay? So that's how you would do that problem. We have to use all of these, F sub F in the x direction, F in the y direction, and the torque all work together to help us get rid of things that we didn't know to get the thing that we did know. All right, the beam with a pivot on its left end is supported from a rope on the right end. In which direction is the force of the pivot on the beam? So the beam is just sitting there, right?
Yeah.
All right, that should help. What do you think?
Because the normal force, right? Because normal force is perpendicular to the surface in which it's, facing.
Is the beam moving?
No.
Is it rotating?
No.
Okay. Do a sum of the forces and a sum of the torques then.
Yeah. We have
So F net has to be 0.
This would be D actually. Wouldn't it? Because then you have an tension.
no, the weight's down. The tension's up, the weight's down. Sum of the forces in the y direction equals
0.
weight down, tension up, and that's 0.
Okay, right. So we would have a weight down off of the center of gravity somewhere, right? I probably didn't draw that in the middle, but the intent was. So we have a weight down.
Well, since it's in the pivot point, wouldn't the center of gravity be on the no, never mind, that's
So
dumb.
then it would.
Is there a force on the pivot point? In which direction is the force on the pivot? There must be, right? Because that's what we're looking for.
So it'd be A.
So there must be a force on the pivot point. Which direction would it have to be going?
A,
If the beam is not moving,
then B, up.
No, because then you have more force pulling it up. You should do it pulling it down.
Well, tension's up, right? Can we label that? Tension of the string is up.
okay, sure, we can put that on there. We kind of implied that with the rope. Okay.
So it's A or C. Because since it's touching the wall, there has to be a normal force.
All right. Is there anything else going on outside of the pivot that would be at an angle? No. So then, action and reaction pairs. Is there anything pressing into or pulling away from the wall that would cause there to be
No.
a horizontal component at
So
the
there is
wall?
no force.
If the answer is no, then it can't be A or C or E.
Huh.
Okay? So it has to be either B or D. Which one makes the most sense? B. Yeah. So the rope and the pivot are supporting the weight of
Oh, yeah.
the beam.
When you say it like that, that makes much more sense.
Yeah. The only question is, was there anything pushing the beam into the wall or pulling it away from the wall? And the answer is no. So we don't have any horizontal components here. So it's just strictly up or strictly down. So there you go. We're done.